Please let me know if the sound is off, too loud, too low. I can adjust it. So, a little bit about me. My name's Joseph, and I have been doing some studying and research over the past decade, and the whole time I've been refining this idea, this little machine that I want to build, and after 10 years, I'm to the point where I've got everything mapped out. I've got the exact experiment that I want to be performed, and many of the kinks have been worked out. So now I'm approaching the phase where it's time to actually build the device to perform the experiments. And if if there's any sort of if we see something in the experiment that hints to some of these ideas that I'm having, then we might just have a really good starting point for for a warp drive. I mean, it sounds ridiculous coming out of my mouth. I'm still having a hard time with it, but there should be a way to do it. I mean, the math is telling us there is. We've had a lot of bright people, working on space-time metric solutions that shows that a warp drive is possible, and it's gotta come around sometime. So I think to start off, this is a pretty crazy idea. I'm gonna have to do multiple streams to kind of fill everyone in, and then also I'm gonna be getting a Patreon going to maybe get some help. So I have reached out to many different possible institutions to help. I live near Oregon State University, and I also live near the Department of Energy, and I've talked to them, and I've also reached out to the Institute for Advanced Studies in Austin, Harold E. Putoff. Tried to solicit him maybe for some research money, but lo and behold, most of these institutions, they want to know exactly how are we going to make money off this, essentially. And so I'm not, what I'm building is not a finished product. What I'm building is not going to be a starship. What I'm building is a apparatus to test some phenomenon out there that I've noticed that I think might be, might give us that first little direction on how we might actually pull this off. And it might do absolutely nothing, but, A for effort, right? So I think to start off, really, I want to start off with some of the basic things that this apparatus includes, because it's kind of a multifaceted device. So I want to start with, I think the best starting point for understanding this idea is to understand sonoluminescence. Now, before I lose people there, because that's, sonoluminescence has been one of those things where there's been a lot of claims around it. It was a really hot topic in the 90s because there was a chance that fusion might be happening in the bubbles. But all of those experiments were inconclusive, and we never found any evidence for fusion as part of sonoluminescence. So it kind of died down. It was just shoved back under the rug. And in the 90s, that was its second big appearance. It's when it was first witnessed, I believe in the 30s, in the late 30s, is the first time sonoluminescence was witnessed and documented. And it later on, the fluid dynamics around bubble cavitation, they had to be studied more in the 40s and the 50s for military applications, because the submarines, the propellers on the submarines were creating a lot of radar noise, and the United States military wanted to figure out how to reduce that signature or eliminate that signature. So a lot of technical work was put in on understanding bubble cavitation in the 40s and 50s to make those propeller designs. And then a little bit later on, someone had isolated a bubble, and they had, kind of, it's what's referred to as single bubble sonoluminescence, and they, oh man. So after single bubble sonoluminescence was seen, it's a very, very easy to replicate experiment. A lot of people, a lot of physics students out there, they'll use this as their easy thesis, right? You can just set up a sonoluminescence rig and get that easy A. So I think that's the place to start. But I just wanted to give out a pre-statement and say that this topic of sonoluminescence in relation to my device does not involve any claims of fusion. That is going to be, that's not where I'm going with this. So I don't want anyone to be like, oh, he's just going to repeat what we learned in the 90s. So I'm not going there. But the process of sending sound waves through a fluid to interact with a bubble, that's more of the core that I'm taking from sonoluminescence. Plus, there's a lot of studies that I'll talk about that we don't know. To this day, there's no generally accepted, like, this is what sonoluminescence is. There's a lot of different theories, and none of them have really been proven as that's what it is. So the original theory, well, I'm getting ahead of myself. I should start with the basics of what sonoluminescence even is. So I brought up this isn't my work, this is just some material I found off the internet, but it's a good basic visual for everybody. So essentially, what you do is you take a small spherical glass beaker, and in the most basic of setups, you're just using water and air. And so first off, what you need to do is you got to prep your water. You got to degas it. You have to filter it, and it works better when the water is as cold as it can possibly be. And so then how the experiment is done is you take a you take an ultrasonic transducer, and you epoxy them to the left and the right sides of this spherical container, and then usually there's a microphone transducer on the bottom, and that's so we can know what the beaker's vibrating at from these two things. And what we'll get is, I want to look at this chart here. This is a good chart. So what we'll get is, goes a little something like this. So you've got your spherical beaker here, and then you've got your transducers, and you got your little microphone transducer. And the goal here is, so if this is here, if we have this going to our screen, it's giving us the data, right? It's giving us the sine wave or the vibrations of this thing. And then these, of course, what we're doing here is we're inputting some sort of signal. So, and we'll just say that, we'll just kind of make up values as we go, but the goal here is to find the resonant frequency of the whole beaker. So like if you hold a wine glass and you sing to it and you find that note that makes the whole wine glass kind of, shake like this, right? That's what we're looking for here. So when you found your resonant frequency because you got your microphone transducer here and you can look for those spikes. And so let's say we found our resonant frequency and it's like 24,000 hertz. So that's an ultrasonic signal and that's our resonant frequency. So when this is vibrating at its resonant frequency, the whole container is like, it's like if a subwoofer surrounded you, and so what we get are these inward traveling compression waves of in the water. So because sound, is just like of the medium that it's made out of. So then what is done is you take a syringe or a pipette and you introduce a small bubble into the center. Now all this takes quite a bit of fine tuning, but it's a relatively easy physics project. And once the bubble's there, it's not going to float to the top because these compression waves are keeping it trapped in the center. And when you fine tune it just a little more, you can get this bubble to cavitate or implode. And when done so, it'll emit a very brief flash of light each and every acoustic cycle. So now if we look at the chart, you can see here this sine wave, that is the 24 kilohertz sound signal. That's the sound wave traveling through the fluid. So, and then this other line here, this is going to be the bubble radius, and then also the applied pressure. And so we can see that each and every acoustic cycle, so 24,000 times a second, we've got this bubble rapidly expanding. I mean, this is a huge expansion relative. I mean, it's a small bubble. And then we have this violent collapse. And so at the time when we were first studying this, our measurement equipment wasn't like as good as it is now. So most of the early research on single bubble sonoluminescence was just done with red lasers. And the measurements that we were getting are pretty much saying that, okay, this flash of light is correlated to the bubble's minimum radius. And so the initial theory put forth on all this was pretty simple, and everyone liked it. I really liked it when I first read it, and that's just that the gas is being compressed and then it's ionizing, and that's the light that we're seeing. And so, but everyone was really, so the thing is that with those lasers, you kind of miss out on, I don't know how advanced, I don't know how technical. So I guess we should go on to, so this just doesn't work with water and air, okay? So, and also the properties of the light, like its brightness and its intensity and things, they can be different depending on what combination of fluid and gas that you use. So after single bubble sonoluminescence was seen and then isolated, then people started changing up the fluid. So they might use sulfuric acid instead of water, and they might use a heavier noble gas or a gas mixture instead of air. They might use xenon. And so the different bubbles, so here you can see they're using the laser. I've got some videos too that I'll throw up. Here's like a long exposure. Sometimes when the bubble, when you don't have it perfectly trapped in the middle, it'll kind of float around and make these cool little tracers. And yeah, and so, another thing to keep in mind is that just like with any, so from what I've read, the expansion and the collapse of the bubble is said to be an adiabatic process. So we can think of the gas inside as kind of isolated and not being able to transfer any energy. So apparently the bubble wall and its speed makes this process adiabatic. So when we see this huge expansion of the bubble, I mean, this is like the bubble's equilibrium radius is this line right here, and when that sound wave comes through, the bubble's able to expand a lot. And so that's going to cool the gas. And then we see this rapid collapse, which is going to heat the gas up. And then, our early theories were all just, it ionizes somewhere around here, and we see this flash. But I was reading some other papers, and, there's something strange going on here. Like, for example, let me pull up the other documents here. Here we go. Magnetic field coupling. So these guys, they saw that they could couple they could affect the properties of the bubble wall with by applying magnetic fields to the to the point where the bubble is, right? So they're kind of concentrating magnetic fields where this bubble is, and they found that they could actually couple the process in a way as to kind of, based on what they were doing with the field, they would have to kind of retune things over here. So they did see that there was this is definitely like it's something you can couple to with a magnetic field, and that was huge to see that. That was really cool for me. And they kind of just go over, every paper on sonoluminescence is going to be like, here's kind of what we think and here's what we saw, and then here's how what we think and saw works with like the four main kind of theories about it. And I mean, there's the theories on this stuff. It's funny because they're all over the place. I mean, so you've got your Occam's razor, you're ionizing a gas. You've got ones that say it's all about the expansion cycle and that it's actually a cold condensate that gets, its environment. It can't be a cold condensate as that bubble collapses, and so then it releases its latent heat as light. I've seen ones to say that it's more related to like Chernikov radiation, where you've got, but not exactly Chernikov. There was a paper here. They did a 3-part, and they called it PTA, and these are some guys' names. They're really tough names. I'll find them. But this is like kind of related to Chernikov radiation, and the pictures, man, the pictures are always so cool. It's just awesome. And see, they only needed one. Like, I mean, you really only need one transducer, because you just gotta pump in the resonant frequency to get the whole thing shaking. And so that's something with my device later on. I've got like 8 transducers on it, but I mean, I might only need one. So, so here's kind of like, when you use different gases, you do get different intensities of lights. When you use different fluids, it's different. And so all this was just fascinating me. And And then I saw that, there's some papers that talked about how you don't even need a spherical container. Like you can just use a cylindrical tube, and I probably have some pictures of it. Let's see. Good thing I got all this indexed, huh? Let's see. There it is. Luminescence. And well, I can't seem to find the exact paper, but I'll have to start finding these and linking them to the chat. No, oh yeah, chat. Speaking of chat, no, I'm not doing a master's degree in optics. So a little history there. I don't have a degree in anything at the moment. I've done about 4 years of chemistry, a little bit of physics, nothing really high up. My job is I am chief chemist at a cannabis extraction facility in Oregon. Um, so my day trade is just some pretty basic organic chemistry, but my interests, my readings, once you learn the basics in school. I mean, once you learn the principles and the basics, you don't you can figure your way out around. I mean, it's all about the information that you choose. As long as you keep it tight and you're reading good stuff, then you can get somewhere. Okay, so yeah, you don't even need a spherical container. So all of these kind of things that I thought were needed, and limitations to eliciting this weird effect. I thought it had to be spherical, it had to be like this and like this and like that, certain fluids and gases. But it turns out you can use a plethora of shapes. You can use a plethora of gases, of liquids, and no matter how you do it, I've seen people, they got flashes of light and they were using, their sound signals were taking less than a watt of energy. So it's it doesn't take a lot of energy to really witness it either, which is cool. It's not like some of these other really complicated things that you need a whole room. Excuse me while I let my dog out. This is one of those things where a lot of you amateurs out there can just set it up in your garage. If you want to see sonoluminescence for yourself, if you want to play with it, there's a lot of documentation on it. It's like I said, it's used as an easy A in physics a lot of times. It's that easy thesis, and it's fun to do. You get some cool results. It's like an interactive experiment, and it's still something that's unknown. So I mean, there's fun there. So, okay, next up is going to be what are kind of like the main theories and explanations. So, of course, I kind of went over already the hot plasma. That's pretty much the basic, it's just hot plasma. Just compressing the gas and it's ionizing, nothing special, nothing to see here. And then one I thought that was really interesting, and I don't have a digital copy of this. I tried to find one, I tried to get one. I'll just have to buy one, but I do have a physical copy of it. And this is Understanding Sonoluminescence by Thomas Brennan. And, he's got some really interesting points, and I think that what he's laid down here is kind of what's opened it up for a lot of these other studies. Like I know that those papers, these ones here, they reference him. In fact, there's a great chart in one of these papers. It's just a freaking awesome chart if I can find it. It really, here we go. So it's kind of like, what their theory explains, what it doesn't, and then down here towards the bottom, you can see that they mention Brennan's idea, and it's also compatible with the theory that they're putting down. So I'll just leave that up. It's pretty cool. So what Brennan points out is that when we're using when you use a red laser to measure that bubble minimum, your quantum, how do I put this, your resolution isn't going to be as good because you're just using a really, really, really thin spectrum of light. You can get a little more information using full spectrum or white light. So what he did is, I thought it was really ingenious. He set up the standard, the basic spherical glass container, water, and I think he used helium as his gas. And what he did is, instead of using a laser, he used a technique called Schliering imaging. And this is when you take like a small white LED and you reflect it off of a large parabolic mirror. And what he did is he set up the experiment to where the light cone was right where the bubble is in the experiment, and then he had his photo multiplier detector on the other side of that. And so that opens up, that kind of lets you see a little more detail on the very bottom part of, so I guess I should go back to that first graph. I gotta start leaving my things up on his tabs. What's this one? This is like, I just need a visual of that graph. Well, so you know what? I'll just draw it. I don't need to know what's going on. So that graph was like, it had that kind of equilibrium radius, and then bam, it expanded, and then it broke down, and it kind of jerk, and then, boom, and do another expansion cycle, right? And then you kind of had your sound wave with like the low pressure and then the high pressure, right? Something like that. And so right in here with those red lasers and how it was timed up, like right in here, we really don't get too much information. So, when the red laser is used, it just pretty much looks like it in the data. It looks like that flash is happening at the bubble minimum radius, which is going to be like, okay, it's a hot plasma. But when Brennan used the Schliering imaging to set it up, he got to kind of see a more accurate like time scale of when that flash was actually happening. And he found that the flashes weren't occurring at the minimum radius. In fact, they were occurring 50 to 150 nanoseconds before the bubble minimum radius. And so he has some plots here, some actual plots, and I'll get a digital version of this. But in the very back, he has his plots from his tests. He actually plotted it and showed that this flash of light isn't really lining up with bubble minimum radius. So he kind of, he's thinking, well, if it's not hot plasma, then like what kind of phenomenon are we seeing? And so that's when, oh, here's kind of like a graph of the um, Schliering imaging setup. My camera's terrible, I know. And so using the full spectrum of light, he's like, all right, it can't be hot plasma. So now, what's kind of like the elephant in the room here is this like giant expansion phase. I mean, you know, it's huge, and since it's an adiabatic process, we can literally treat the gas inside it. So as soon as that boundary expands, that gas is just cooling down really fast. And so that's when Brennan comes in and he postulates that the gas, when it's cooled like that, it actually becomes an excited cold condensate. It actually kind of becomes, I guess it would be like a Bose-Einstein condensate. And so you've got this state of matter. So the gas is just like slammed into this quantum state of matter, and then as the bubble starts collapsing, and I mean this process is so fast. Well, I mean when you do the calculations and you look at the speed of the bubble wall, I mean it's like crazy fast. And so somewhere around, 50 to 150 nanoseconds before the true bubble minimum, we're seeing this flash of light. And so he thinks that when that cold condensate, when it turns back into a gas as the environment isn't suitable for it to be a condensate anymore, when it turns back into a gas, that's when we see the latent heat get released as light. And so that was really cool. That kind of turned everything on its head. It was a really cool study. He had linked it into a few other phenomenon, and if you're into it, you're just gonna have to read his book, or his paper, because it's really cool. And so and he does say that one of the related phenomenons is like, like when you have something going from a high pressure gas chamber, like if we had a bunch of high pressure gas and we had a valve that just emptied into a vacuum chamber with a really high vacuum, we could create this excited condensate at the nozzle tip. And I forget what they called that. And of course he does, like I said, there's rarely a sonoluminescence paper out there that doesn't touch on fusion topics, but I don't want to go there until things, I just don't want to. I just want to stay out of that. I'm just interested in the power of sound, and maybe there's some tricks with sound that we don't know yet. And one of the things, after reading Brennan's idea, I started really thinking about this expansion phase. And of course there's always this funny little dribble that you'll see. There's always like a bam, and it kind of like boom before the big expansion. There's kind of like a little vibration. But the light, the flash of light, it only shows up after the main expansion. And I think that's what one of his main points was that we don't see when this drops, and then it kind of to the next one. We don't see flashes through any of these. We only see a flash somewhere in this time zone, before the minimum. So we'll see our flash somewhere around here. And so I thought he brought up some really good points. And I was just kind of sitting on that for a long while. And I read another paper recently that I thought was really, really interesting. And I'm just going to take like a small digression, just a really brief digression. But this paper was really cool. So now I'm still trying to wrap my head around this one a little bit, just to make sure I'm understanding it correctly. But it looks like last year, Alberto Nicolis. Oh, you know what? I've got a digital. I've got this paper digital. What am I doing, dude? I'll read them to you guys. Right here. Okay, that's the thick one. There should be like an easier to read version here. Yeah, here we go. Okay, so what they say is that they analyze the behavior of sound waves moving through superfluid helium, and waves carry a small amount of mass, and phonons, the quantum units of sound waves, interact with a gravitational field in a way that requires them to transport mass as they move. It's kind of like an inherent thing where. So what they say is what they found is that they found that the sound waves themselves do carry mass, and for a 1 second long 1 watt sound wave in water, the amount of mass would be about 0.1 milligrams. And they quote right there, they think it's honest to God gravitational mass. I mean, this is a pretty bold claiming, but this paper, this is like the layman's version of this paper here, where you can see the nitty gritty. And so that just got me thinking a little bit. I was reading this topic and I was thinking, man, I wonder if this has anything to do with sonoluminescence, and if there's because then what I'm thinking of, if sound waves are carrying a mass, and then you got this this concentration of apparently negative mass that's occurring at the center of this glass beaker, and it's occurring where this air bubble is, and then we're seeing something we don't understand yet. So I thought that was really interesting. And I just wanted to throw that one in there so we can all just keep in mind. It says here that they estimate. Here, I'll scroll down if you guys need to scroll down. But they estimate that the mass carried by a sound wave in a Bose-Einstein condensate of extremely cold atoms, much like the state of the gas that Brennan describes in the expansion phase of the bubble. A condensate of extremely cold atoms could carry as much as 1 part in 1,000 of the total mass of the system. So I'm thinking to myself, okay, if we might have a way to, with sound, to kind of play with. I mean, if we can kind of create little negative mass values and jiggle, like, I just think there's got to be something cool that's going on here, especially when you think about the total mass of the system. It's like, well, what with resonance and things. I mean, we already know that electromagnetic induction is a thing. It's like, can you resonate with systems of higher energy using a technique like this? Using these properties of sound that we're just now kind of finding out. So these are all really sweet papers, and I don't know how to link files to the stream chat yet, so I should probably figure that out. But I digress. So back on track. Let's see, stream outline. We talked about all that. Talked about the magnetic field coupling. Okay, so that's pretty much, that's the big mouthful. That is sonoluminescence, the history, the basics, kind of where we're at currently on understanding it. Not much progress has been made. There's not a lot of money in that field. There's nothing going on there. So next, here is kind of where my thoughts really start coming into all this. And you might like the way it goes. So what I want to do is I want my glass container to look like this. So instead of using a spherical glass container, I want to use a toroidal container. And the bubble, instead of being a spherical bubble, I wanted to do a ring bubble. And I was trying to figure out how would you get a bubble ring in there, because we all have seen the easy way to do a bubble ring, which is just get underwater and blow a bubble. I got some videos here. They're really cool. Oh man, videos, boom. Let's type in bubble. Sweet, so here's like, oh man. So bubble rings, just on their own, fascinate me. Like, holy cow. Talk about just what a trip. And they're really stable. They're really stable objects. I'm sure we all seen the funny one where the jellyfish gets wrapped up in it. They're really strong, they're really stable, and you can see this cool thing happening where there's these little like modular bubble bits, but it kind of like retains the shape. It's so cool. Like, what? That is just so cool. Here we get to see kind of a slow motion, really good one. They're just like so majestic. I don't know what it is about them, but like that, especially how they can be all modular and then they smooth out and they can go modular again. They can connect, reconnect. You see that one there had like a little triangular oscillation in it. Look at this. Look at this one here. It's like you can totally see it. Oh, right there. Boom, boom. You see those triangular tips that formed on that one there? That was awesome. So what I want to do is I want to perform sonoluminescence, but I want to perform it on a bubble ring. And so I guess the most basic of thoughts I had was be like a timing based setup where you like let the bubble ring float up a cylindrical container, and then you either drop the container onto a surface or you run some sort of sound wave through the container, as that thing's coming up as it comes through the sweet zone. But all that was like really complicated, and I was like, I want something more controllable and tunable. So I was looking for a way to like make a bubble ring in the lab. And then also, kind of as I was formulating my ideas, I was I was taking some thoughts from Brennan, and here's some notes from Brennan's work that he found from his experimental evidence. He says first he made a really nice formula where you could know the energy of the condensate. Um, and based on the formula and based on his experiments and the stuff that he came up with, he made a list of properties. And he says that the formula predicts that larger bubbles will have more energetic discharges, and that cooler ambient temperatures and higher static pressures will have brighter, more energetic discharges as well. It hints to lower frequency resonators with larger bubbles as being like, more energetic. And, of course, like I said, every paper on sonoluminescence is going to have something like this in there. Possible for condensate energy to exceed 7 gigaelectron volts. Enough for fusion with the right isotopes present? Question mark. We're not going there. Not yet, maybe in the future, but right now, no. So the bubble emits a single bright flash once per acoustic cycle, and the typical drive frequencies are in the upper audio to ultrasound range, but sonoluminescence is known to occur from low subsonic frequencies all the way to the megahertz band. So we really have a lot of experimental freedom with this, which I really like. It's going to be really cool. So starting from equilibrium radius, the bubble expands to a volume that is more than 100 times greater than its initial one. Then the bubble suddenly collapses and bounces several times at about 50 to 100 microseconds. Wait, that's ns. Okay, it's nano, sorry. Nanoseconds before the first minimum, a brief flash of light. So another thing I didn't touch on there was the duration of the pulse of light. Very fast. It's 100 picoseconds in duration. And so we just get that one quick little flash on the first collapse from the expansion, and then through all the bounces we don't see it again. And then once again, the expansion and collapse of the bubble, both are adiabatic processes. So, with all that in mind, a bubble at room temperature with an equilibrium radius of 8.5 micrometers will expand to a radius of 63.8 micrometers with a temperature of about 5.3 Kelvin. So just as a cool way to cool gases down, I mean, that's pretty sweet. I mean, which makes it just made me lean towards kind of that cold condensate, where maybe this isn't as simple as a hot plasma. It could be like another kind of state change that is causing this. So I've never seen anyone go for a bubble ring, and in the meantime, just studying the properties of bubble rings, kind of getting into that a little bit was really cool. There's super cool. So Brennan mentioned that cold air temperatures are a plus, and as we know in the standard setup, the colder the water is, it's a plus. And so what I want to do is I want to use, and I don't know if this is how this is going to be designed. This thing being attached here might be a dampener problem on this. So I don't know if I'm just going to use one little hose bar port coming out the side, or I want to make this attachment as minimally, I don't want it to affect the vibrational properties of this ring, because it's going to cause this weird thing where so this little bit might have to be changed, but this is just early illustration purposes. So these hose bar ports is how I would be getting fluids and gases into the tube, and then also I'd probably hook one up to a vacuum pump, so I can kind of control vacuum pump and air pressure tank, so I can control like the amount of or lack of pressure in the tube. So I was thinking, so how am I going to get a bubble ring in this? I want to use a fluid, and I want that fluid to be spinning around the tube. So imagine if we filled this tube up. If this is like a little crow section of our ring, and if we filled this tube up with a fluid, so we've got our fluid, but we left a little bit right here. We left a little pocket in there. And let's say, let's say that this pocket we chose helium. We're gonna put we got a bunch of helium gas up in this pocket, right? So that's kind of like when everything's still and you fill up the tube, you've got the helium gas here that you've put in, and then your fluid is down here, right? This is all your fluid down in here. Okay, so just to spill the beans a little bit, but the fluid that I'm choosing is going to be liquid oxygen. And so of course, this is going to have to be, I'll kind of show you a more, this will have to be in a case. So, this experiment's going to have to be submerged in liquid nitrogen for this to work. So I'm just saying right now that this whole ring that I had up, the whole ring would be like submerged in liquid nitrogen. So that way the liquid oxygen on the inside, it's not going to want to do anything. It's not going to want to pressurize the tube. It's not going to want to evaporate or do anything. It'll just stay liquid oxygen. It's going to be sweet. So like I said, we got a bunch of helium up here. And this is just a crow section of our torus. So now liquid oxygen is paramagnetic. So you can literally propel liquid oxygen down a pipe with electromagnets. Like, it's sweet. And there was a paper liquid oxygen pumping. So it was old NASA one I found, because when I had the idea to use liquid oxygen, I was like, I'm pretty sure I could propel it. But it's always good to see something out there when you have the initial thought. And this was kind of far down. Pumping of liquid oxygen by use of pulse magnetic fields. So this is kind of where I saw, okay, you can take, they had some coils, and they just kind of had they just made like an L pipe, and they had the solenoid wrapped around the tube, and it was all submerged in liquid nitrogen, and then they would pulse the coil, and then they would measure how far up the coil that liquid oxygen would go. And they even say towards the end that you could transport it this way as well. Right here, multiple solenoids with synchronized delayed current pulses were also simulated, suggesting that multiple stage solenoid coils could theoretically propel liquid oxygen to any desired distance. So what I want to do is have some electromagnets around this torus, and that way I can start pushing the liquid oxygen around. Now, there's some challenges there in itself. One, you got to have some pretty smooth flow to get a bubble ring, and we all know that smooth, laminar flow in a closed system, especially one that's just essentially an ever long, it's just a turning pipe, it's just an infinite turn. So, huge challenge there, but I'm gonna, definitely still think it's possible to get the liquid oxygen flowing around that thing in such a way so when it's on and we're propelling the liquid oxygen, that our system should change to the new low pressure, the new low pressure region of the system when everything's flowing nicely would be the center is going to be your low pressure. That's where all your gas is going to displace to. And then your highest region of pressure is going to be, the outside here. And that's where you're going to have your liquid, and your liquid's going to be kind of like, like spiraling around it. So all your fluid would be distributed on the outside, and you'd kind of have like, what I'm hoping to have is a bubble ring, a nice bubble ring where the magnets are driving the fluid around, and like I said, all that gas. So then you have a nice bubble ring kind of trapped here, and so then we would add transducers to this, and we would see if we can actually perform sonoluminescence on a ring bubble. And that's really as far as that's really that's really the core of the idea, right? I mean, that's pretty much it. So I can't really say any of the other ideas I've been having. I can't say any of those hold any weight until I've at least set up it to this point. So I don't, I'm kind of the point where I don't even want to talk about the later stuff until I know that it's even possible for me to make a ring bubble in a system like this. So I would say the first chunk of this experiment is really just going to be able to see whether one can use liquid oxygen in a closed system and create a bubble ring that's just nice and right there. And so that's going to be the phase one of the prototype. It's just, can the bubble ring be created in the device? And then if so, that's when we're going to roll on to, look, I totally ignored my picture. We're going to roll on to some ideas where you don't use gas as the bubble. And I want to see if it's possible if I can create a vacuum bubble. So, and that all is just going to come with experimentation. I don't know whether that's possible or not yet, but I was thinking that if the liquid nitrogen is 77 degrees Kelvin, and then the liquid oxygen won't want to turn into a gas, I think, until almost 92, 97. I should check. But there's like there's like almost a 20 degree Kelvin difference. So I was thinking, maybe, is it possible to omit any gas and just, omit the gas and, like take the chamber to, and like fill it up with the liquid oxygen and then like vacuum out everything else, but maybe not so strong of a vacuum, because obviously so strong of a vacuum is just going to cause that liquid oxygen just to turn into like oxygen vapor, I guess, which might be really cool. No one's done that one yet. But I'm thinking, and I'm like hoping that there's like kind of a Goldilocks zone where you can have like a vacuum bubble and like just have it be totally devoid of any gas and or oxygen vapor. And why I'm into the vacuum bubble idea, because that's kind of the cool cool thing about this apparatus is that you can, once you build the basic setup, and here I'll just give you all a sneak peek. So I'm not going to leave it up for long. It's just going to be a sneak peek. And this is like in the case with, this is it right here. Oh yeah, I had these rendered as brass. Just ignore that. But that's what it would be like, something like that on its stand. In its case, using 10 gauge wire. Here's like, this would be the size. So this is like the size of the whole thing. This is like the actual size. It's not very big. And then this would be like the size of the actual, the actual torus. So this is the full ring with the thing coming out the side. And then this is like the glass wall here. Some pretty thick glass. And most definitely going to be using some very high quartz content bromosilicate, like the highest I can find. And I have a glass blower. I have a glass blower in Portland that I've already talked to. He's ready to make these shapes for me as soon as I'm ready. So I told him that I got to get the stream going. I'm going to try to get some Patreon support, and maybe actually be able to make some really cool content building this thing. So, and definitely with the nature of the device being something so cool, I wanted to make it open source, and I wanted to stream and really share as much as I feel comfortable sharing. Obviously, at some level, I have to protect my secret sauce. But when the build gets to that point, let's say, people are into this. Let's say I can get some public funding, because I can't get funding from the other sectors. I don't have a degree, and it's all like trash out there. They just want to know how to make money off your invention. I'm like, what happened to making experiments, dude? Like, anyway, so I'm going to be like recording the builds. I'm going to be live streaming the builds. I want to, really stay in the public eye if I'm going to be, continuing this. And, it's just going to be fun. Like I said, stage 1, we're just going to see if we can get the liquid oxygen to flow around there and see if we can get a nice bubble ring. And then if that's possible, then the experiment's going to get really cool. And we're going to see if, because it's just that's right, I got to show you, vacuum bubbles are weird. Like, if you thought ring bubbles were cool, vacuum bubbles are strange. And I thought a ring, like, a ring-shaped vacuum bubble, I mean, that just is screaming something sweet. Where is that video of the dude who has the vacuum bubbles? Let's see, it's right here. Videos. Oh, I conveniently put it in the folder it needed to be already. Look at that. Oh, here was like this was a pretty cool one. So in this one, they've got water in a tube, and they just kind of, it's huge. Let me get that smaller. So in this one, they just have a tube like on a Ferris wheel thing, and they're just like spinning the tube, like Wheel of Fortune or something. And so we can see this cool thing where, you do kind of have this twisting, this like low pressure twisting in the center there. And so I saw that and I was like, well, this is great news. Given that this kind of rotation, the way this is set up, it's like more of a natural system. So this is like more likely to happen with this like kind of, more smooth spiraling flow there in the center region. There may need to be something like this going on, because, using like electromagnetics to drive the fluid as the way to get a smooth flow is like, that's just a terrible idea. So, I mean, I was even imagining things as far as having like laser Doppler velocimeters, like track the properties of the fluid near the center, feed that into some, machine learning algorithm that can just, I don't know. I've got a lot of complicated ideas. Like I said, I want to start in the most basic ways possible. So, it might just come down to putting the glass tube in there. It's submerged in the liquid nitrogen, and then like there's an electric motor that spins it, right? Um, and then we can figure out how to get the sound waves onto it. Obviously, you can't use transducers at that point because then you've got this spinning object with wires attached to it. So, I think all can be figured out, though. Of course, all can be figured out. So there's a lot of ways to kind of get to this idea, and so I thought it'd be fun to just include everyone on the adventure, and also use that platform as the way to pay for the experiment. Okay, but I was actually trying to find another video for you guys. That's really what, and it's a really cool one. It's going to be in information archive videos, and then I'm going to search that. Here we go. Yeah, this is great. This is just like this was one of the coolest things I've ever seen. So, does he give you the little setup here? He'll give you the little, let me get some sound for you guys. If it's too loud, let me know.
Keep it nice and clean, I do it in a single all-glass apparatus, cutting off the vials with an oxypropane torch.
What is this? So right now I'm just showing a video of vacuum bubbles trapped in sealed glass containers. So this guy, he distills his own
that
water.
When you're finished, when you've done all of that,
I think you guys can
looks
hear it.
like a spider, and it's a completely sealed kit under vacuum
explain
with
it
some
really
water
nicely.
left in it. Now the thing is, there's almost no air left in it
stuff on frame
whatsoever.
while you
It's
guys
a
are watching
vacuum,
this for a
which means
second.
that the space above the water there's only water vapor. And if you shake it, it makes this weird clink, clink, clink sound. So normally when you have a bubble of gas in glass, it looks more like this.
So this is how water behaves. This is now open to the atmosphere. So what you'll find is you can actually get a bubble in there if you work at it. This is regular water. Right, but what you'll find is that bubble is really pretty non-compressible. Right, it doesn't move around much. That's because there's actually gas in here, and for this to move up, the gas has to be compressed. So we can actually bubble out. So that's what water looks like, an air bubble looks like under atmospheric pressure.
And this is what it looks like filmed at 1000 frames per second. So when I start shaking it, you can see there's actually water moving around on the inside of that bubble, but the bubble's not really compressing much. Even though there's really quite a lot of agitation on the water here, the actual volume of that bubble isn't changing much.
And this
But when
is how it behaves.
it's a vacuum in water,
You see the
check out what
bubbles.
happens. And
It
now I
actually
know this is
goes
probably because
almost
there's water
nothing,
vapor
no effort.
in the regions that are vacuum,
Move this around a bit.
but still the effect is sweet, and I feel like has something to do with all of this.
And here it is, again filmed at 1000 frames per second, with a
And then
similar degree
he'll
of
slow it
agitation.
down a lot, and
So you can
get
see
to
that
this
little bubble, its
nucleation
volume changes hugely with the same amount of shaking. And that's because there's essentially no gas in that bubble, so it can compress a huge amount. So that's kind of each other,
And the
such that
sound,
when
right?
one
It, like,
bubble
makes a
collapses,
clinking
that's
sound.
the
So here we
bubble
see some
compressing.
super
And what you're
slow-mo.
going to see is when that bubble collapses completely, there are all these nucleation sites that just appear throughout the liquid, just like that, and it's amazing. And so some of them, they actually sort of bounce, and also the bubbles can sort of talk to each other, such that when one bubble collapses, it actually creates more nucleation centers. And it's just amazing.
So I just thought it'd be really interesting to see what
with that,
happens
I'm
when
going to
you're
edit this down a
performing
bit such that
sonoluminescence on
you
one of
just
these
see the
vacuum
bits where it
bubbles.
actually nucleates. Because if I didn't,
how,
even though there was only about
you
4
know,
or 5
can it still
seconds of video
nucleate
actually
like
recorded by
we're
the
seeing
high-speed
here?
camera, it would take you over 40 minutes.
Can it still nucleate when it's in this environment where the sound waves are concentrating it? you know. So
So what
maybe
did-
even a more basic experiment would just to be set up a spherical container and still use the liquid oxygen and try to get a vacuum bubble, you know, or even just try even the basic, just water and a vacuum bubble and a basic solenoid nested setup. So there's a lot of cool ideas, and there's a lot of cool paths or choices you can make on just one apparatus. So, like I said, what I'm really designing here is just an experimental apparatus to kind of investigate some of this stuff. But I really do think that this is the kind of phenomenon that's going to lead us to having these kind of propulsion systems that you know, take advantage of things just we don't know yet. Because I'm reading stuff like it gets into some super theoretical stuff, you know, but I've read a lot about the possibility, you know, like how practical is a warp drive anyway, you know. I mean, right now it's not practical. The energy requirements are too high. There has been some work in designing practical ones where they're kind of like in reach, sort of, but, you know, I think there's a trick to certain states of matter or certain geometries. Like if this vacuum bubble is resonating with some, you know, like extra, you know, like a compactified dimension or something, then like you might be able to like actually create a resonator with some sort of, you know, region of compactified energy that provides you more. You know, I mean, who really knows until more research is done. So that was just really cool. So one of the big things is I definitely want to test out a vacuum bubble in my system. And so for now, you know, like I said, I'll pull that image up one more time. You guys can kind of get an idea of what the machine might look like. And so said here would be the glass piece, and the other renders were older renders. I had the things rendered here as brass, but this would be like, you know, like I said, it in the box. So you would have this full of liquid nitrogen, and then your liquid oxygen would be in the tube, and there's the transducers, there's the driving transducers, these are the microphone transducers. You can see how the microphone transducers are placed out on, they're like on the side. So essentially it was like the basic spherical setup, but like replicated 8 times into a torus. That's kind of how I stitched it all together. It might be that I only need one of these and one microphone, you know, to get the whole thing, but I was just creating some, you know, creative visuals on what the machine might look like. And, you know, this isn't going to require a huge facility. This is going to require, you know, a decent little workspace, some gases, some basic materials at first. Now, I will say that one thing I would like to also test along the way is that, you know, just so for the prototype, I'm keeping it simple. I'm keeping it cost effective. So, you know, I'm keeping it kind of, you know, cheaper for now, but really what I want to do is I want to have the coils be, instead of copper, I'd like to use high temperature superconducting ribbon instead there, and, you know, see how that works even more. But that brings in a lot of extra technical details like flux pumping the superconductor, quenching the superconductor, you know, it's a lot of stuff. So the NASA paper about liquid oxygen pumping, they were just using DC pulses through copper. So I figured, you know, if these coils are pulsing, and they might need to be pulsed linearly, so 1, 2, 3, 4, 5, 6, 7, 8, or we could also use computer control to do pulse patterns. So, you know, squares and triangles and things that kind of give us a smooth flow if just one after the other, creates too much turbulence. So, the initial build and the initial challenges are going to be just, the glass vessel, the copper, the transducers, and some sort of case or tank to submerge it all in liquid nitrogen. And that's all fairly affordable. And I've got a glass blower in Portland who will make these for me, these glass shapes. And so yeah, that's really where I'm at right now. I'm gonna have to head off to work, head to the lab soon. But this was my first stream. I want to keep doing these streams, and I'm gonna share my Patreon. And by this fall, I'm gonna have the glass shapes start being made in the fall. And so I'm gonna keep getting on here and talking about it from time to time. And then once it's time to build, I'm gonna pick a streaming platform and start getting the build videos out and going. So thanks everyone who stopped by and tuned in for a little bit. Thanks for checking out my thoughts and things. Feel free to message me about them. At some point I will need to have a few interns on hand because I'm not a technical math whiz. I'm more of a hands-on. I really like building things, and I've just been seeing these kind of neglected concepts that I think might have something to do with us getting out further into space and things. And so I'm going to go ahead and share that link. I should have had it shared up the whole time, but let's see. Let me pull it up here. It's gonna be my public page, and then I can go like this. Sweet, and I can share it here. So so there's the Patreon, and like I said, I'm gonna be firing up the project in the fall and getting those first pieces built. But please, I would love to hear questions. If there's any really savvy physics nerds out there, and you got some holes to poke at me, you want to talk about some things, I am super open to discussing my device. I really want this to be kind of an open source community effort. So my first draft on the prototype is done, and it's time to build. So I'm really happy that y'all stuck around. And like I said, I got to get out here and go to work for a little bit. But that's it. Thanks. Thank you.